My name is Hui Guo. I'm going to present a joint work with Professor Cindy Rubio on error-inducing floating point input generation. This work will appear in X 2020 in July. First, what are error-inducing inputs? Error-inducing inputs are floating point inputs that trigger a large numerical error in the result of the program. To find a way to generate error-inducing inputs, we first examine how an error-inducing input triggers a high error. So we use a program that implements recursive summation as an example. This program takes an array as input. So we manually crafted an input array. This array can trigger a high error in this program. So in the first operation, it adds A3 to A2. The result is negative 98. And E represents the error in the result. In this operation, the value of A2 is rounded off. We consider that as a severe precision loss. The second addition adds negative 98 to 98. And this is a cancellation. After the third addition, the program computes the sum of all the elements as 1.1 times 10 to negative 15. And the error in the result is negative 1.2 times 10 to negative 15. This is a very large relative error. So our insight about generating error-inducing inputs is that we should explore the operations where precision loss and cancellation occur. We designed and implemented a tool, FPGen. It's an error-inducing input generator that uses symbolic execution. Specifically, it has three components. The first component is accuracy check injector. It injects the program with inaccuracy checks. The second component perform symbolic execution on the injected program and generate a set of inputs that maximize code coverage. And the third component measure error for each of the inputs to identify error-inducing input. So this tool is publicly available on GitHub. First, we describe our first component in accuracy check injector. So there's two checks in the injector. The first check for precision loss. For addition and subtraction operations, we compute the difference of the component of the two source operands. If the difference of the two exponents is larger than a threshold sigma in magnitude, then we consider that as a severe precision loss. To illustrate what does the threshold sigma represents, we use this figure to illustrate that. So each number in this figure is represented in the form of sign, exponent, and significand. And sigma here represents the number of bits that are discarded in the significand of one operand. Second, we check for cancellation. We compute the maximum exponent of operand 1 and operand 2 to the exponent of the destination operand. If the difference of the two is larger than threshold theta, then we consider that as a cancellation. So theta here represents the number of bits that are cancelled out in the significand of the two operands. So we create the inaccuracy check using the two formula. So basically, this inaccuracy check will introduce three branches. One branch identifies precision loss cases. One branch identifies cancellation operations, and one branch identifies operations that are accurate. So because precision loss condition is contradictory to cancellation condition, so there is no overlap between precision loss cases and cancellation cases. Second, we present our second component, symbolic execution. So this module implements an algorithm that iteratively concretizes input variables and executes symbolic execution. So first, we perform a random search for base values of the input arrays. And then we partition the input array into two groups. One group contains the variables for concrete values, and one group contains the variables for symbolization. In the while loop, we concretize the input variables in concat walls, and we symbolize variables in symbol walls and perform symbolic execution. Here, we monitor the status of the symbolic execution engine. If it times out, then we reduce the symbolic variables by half. And if it terminates and generates a set of inputs to cover program passes, then we redistribute symbolic and concrete variables and continue the loop. So we evaluate, to evaluate FPGA, we compared with three other tools. First is a random input generator. Second, S3FP is the state-of-the-art error-inducing input generator. And third, CleFloat, a floating point symbolic execution engine. This is also the symbolic execution engine we used in FPGA. Our benchmark include 3 summation programs and 9 matrix computation programs in C and 9 statistic programs in JSL. As you can see, all these programs take multidimensional input data, such as arrays, vectors, and matrices. The third column and fourth column describe the number of symbolic variables and the number of concrete variables in the initial partition. Here's the results. So basically, on the x-axis, these are the benchmarks we used in the evaluation, and the y-axis represent the maximum error each tool can trigger in the program, and different color represent different tools. Here, specifically for CleFloat, it failed to trigger an error for any of the programs. As we can see that in most programs, FPGA triggers the highest error. There's 3 programs. None of the tool can trigger a high error. And there's 3 other programs. S3FP triggers the highest error. We guess the reason is that probably FPGA cannot trigger cancellation in these 3 programs. To summarize the results, first, out of 21 programs, random and S3FP, they can trigger an error in 13 programs, and CleFloat failed to trigger an error in any of the programs. FPGA triggers an error in 20 programs. Regarding to the magnitude of the error each tool triggered, FPGA triggered an error that is approximately 10 to the -6 on average. So it's 2 orders of magnitude larger than the state-of-the-art S3FP. To conclude, first we design and implement FPGA. And in FPGA, we formulated precision loss and cancellation to enable symbolic execution for error-inducing floating point input generation. And we designed an algorithm that performs iterative concretization that manages the number of symbolic variables to scale symbolic execution. To extend FPGA for larger programs, there's 2 future directions. The first direction is to add more optimizations to further scale the symbolic execution. Second, a direction is to add a search algorithm that automatically identifies operations for inaccuracy check injection.